Welcome to the deep dive. Today we're tackling, well, a really crucial question for our greener future. Electric vehicles, they're essential, right?
Absolutely key.
But what actually happens when millions of them all plug into our existing electrical grids? You know, maybe all at the same time.
Yeah, that's the big challenge.
So we're diving into this fascinating study. It's from the 25th Iranian Conference on Electrical Engineering, ICE 2017. It gets right into this.
Interesting piece of research.
Our mission here is to pull out the surprising facts, the crucial insights, show you how EVs really impact that peak electricity demand, whether we manage them smartly, and even the nitty-gritty of how they actually charge.
And what's so intriguing here, I think, is that EVs offer these, well, immense environmental benefits. We all know that.
Right.
But getting them integrated widely, it's not quite as straightforward as just, plugging them in.
Seems simple, but it's not.
No. This paper really explores that critical challenge. Grid reliability, cost, especially when you need this massive amount of energy for charging.
So it kind of asks, can we actually harness their potential without completely overwhelming the infrastructure we already have?
That's the core question, yeah.
Can we handle it?
Okay, so let's unpack this. The study looked at several scenarios,
Right.
some with and some without what they call demand response.
Exactly.
Smart management versus, well, just letting things happen.
And the findings.
Well-
They reveal a pretty stark truth. Without any smart management, just plugging in EVs willy-nilly could send our grids
No,
spiraling.
it really could.
Yeah.
In one scenario they modeled, the peak demand shot up
How high?
to an incredible 1,272 kilowatts.
Wow. And to put that in perspective for everyone listening, that's potentially more than doubling the average demand.
Easily, which leads to much, much higher costs, up to $742 in their model.
For one charging event.
In that specific unmanaged scenario, yes. It really highlights the scale of the problem if we don't manage it.
Right. Imagine your whole neighborhood suddenly needing twice the power it usually does, all at once.
Exactly. So if we connect this to the bigger picture, the study then explores the solution, this demand response.
Okay, explain that a bit.
Think of it like the grid kind of asking your car to charge at specific times, or maybe even share a bit of power back.
Ah, okay. Smart communication.
Precisely. And the most effective approaches they found, like their scenario 8, showed significant peak shaving.
Cutting down those big surges.
Exactly. And valley filling, using power when demand is low, typically overnight. And importantly, doing this without creating new, different peaks later on.
Okay, that's key. You don't want to just shift the problem. So how did they manage that? How do they avoid creating new peaks?
Well, this was achieved by strategically using something called vehicle-to-grid, or V2G capabilities.
V2G. Okay, I've heard of that. That's where the car sends power back.
Yes, exactly.
Okay.
Even just a small amount. They call level I discharge. Think of it like a trickle charger, but in reverse.
Yeah.
Very low power. So they combine this tiny bit of discharging during peak hours when the grid is stressed with intelligently charging the vehicles after midnight.
When grid demand is naturally at its lowest.
Right. And this brought that peak demand way down to about 616.4 kilowatts in their model.
So roughly halved from that worst case scenario.
Pretty much. And the costs came down too to around $646, closer to the optimal level. It really shows that understanding V2G is important.
And also the charging characteristics. You mentioned linear versus nonlinear.
Absolutely essential. Understanding that difference, whether the car draws power steadily, like a simple resistor, which is linear, or if the power draw changes as the battery fills up, which is nonlinear and more realistic.
Right, because a battery doesn't charge at the same speed from empty to full.
Exactly. Knowing that difference is key for optimizing these smart charging schedules.
That really breaks down the technical side well. But, I imagine some listeners thinking, okay, V2G, nonlinear charging, but my car isn't just a battery on wheels. I need it when I need it.
Of course. That's
Right.
a perfectly valid point.
So how do these technical solutions translate into something practical for, us, the everyday EV owner, without making life inconvenient?
That's the million-dollar question, isn't it?
Yeah.
Convenience is absolutely key for adoption.
Yeah.
The study suggests that while this more realistic nonlinear charging might take a bit longer to finish a full charge cycle,
Okay.
the real power lies in the strategic timing. It's about using those times when your car is just sitting there anyway.
Like when you're at work or asleep.
Exactly. Leveraging those idle periods to interact smartly with the grid. You're not really giving up your car's availability when you actually need it. You're just letting it charge or maybe discharge a tiny bit when it suits both you and the grid.
So what does this all mean for you, the listener? The takeaway seems to be that strategically plugging in your EV during off-peak hours,
Like overnight, or maybe even during the day at work, if charging is available there.
that could be a really key part of the solution. It sounds like it's about more than just owning an EV.
Definitely. It's about participating, becoming part of a smarter, more efficient energy ecosystem, one that helps prevent grid overload and, ultimately, keeps costs down for everyone.
Right, being part of the solution, not the potential problem.
Which does raise a really interesting question for the future, doesn't it? How might these evolving smart grid technologies, combined with our daily routines and choices, how might they completely redefine how we think about energy, consumption, generation, maybe turning our cars into these dynamic tools that actually help grid stability rather than just being another load drawing power?
Cars as active grid partners, not just passive consumers. That's definitely something to think about.